It looks like frozen smoke, so light it can sit on a flower, and so insulating it can shield a leaf from a blowtorch. This is aerogel, a solid that's mostly empty space. Some silica aerogels are over 99.8% air, but how can something so insubstantial be so powerful? Aerogels start life as a wet gel, a microscopic sponge where a solid network traps liquid inside tiny pores. If you just let that liquid evaporate, surface tension crushes the fragile framework. The trick is to remove the liquid without collapsing the pores. Engineers use supercritical drying, often with carbon dioxide, so the liquid becomes a supercritical fluid and escapes with almost no surface tension. What's left is a dry, solid foam with nanometer-scale pores and a gigantic internal surface area. How light is light? Typical silica aerogels have densities around 0.003 to 0.2 grams per cubic centimeter. The most extreme lab samples go near 0.001. For comparison, water is 1.0, and balsa wood is about 0.16. Pick up a piece of aerogel and your brain expects weight. There's almost none. Its most famous superpower is thermal insulation. Heat normally moves by conduction through solids, convection in fluids, and radiation through empty space. In Aerogel, the solid pathways are extremely thin, so conduction is weak. The pores are so small, often tens of nanometers, that gas molecules keep bouncing into the pore walls instead of carrying heat efficiently. This suppression of gas conduction is the Knudsen effect. Combine that with tuned infrared opacity, and you get very low thermal conductivity, often 0.013 to 0.02 WMK at room conditions, far below typical foams. That's why you'll see a torch blasting one side, while a flower on the other side barely warms, at least for a moment. But aerogel is not magic. The same structure that blocks heat also makes it brittle. Silica aerogel is like a glassy sponge. Spread the load and it holds, press sharply and it crumbles. That's why industry often uses aerogel blankets, tiny aerogel granules embedded in fiber mats. Flexible, tough, and still highly insulating. There isn't just one aerogel. Silica aerogel is the classic, bluish and ghostly. That blue tint comes from Rayleigh scattering. The pores are smaller than visible wavelengths, so shorter blue light scatters more, just like the sky. Polymer aerogels can be tougher and slightly flexible, great when impact resistance matters. Carbon aerogels conduct electricity and offer huge surface area for supercapacitors, electrodes, and catalyst supports. Chemists also add silyl groups to make silica aerogels hydrophobic. Untreated ones can absorb moisture and lose performance. Where does it matter in the real world? In space missions, mass is everything. NASA used aerogel to capture comet dust on the Stardust mission, gently slowing tiny particles without vaporizing them. Aerogels also insulate instruments facing extreme temperature swings. Back on Earth, aerogel blankets line cryogenic tanks, pipelines, and high-performance building panels where slim profiles and high R values are prized. In energy and electronics, carbon and polymer aerogels provide large surface area and controlled porosity for batteries, supercapacitors, and sensors. Even acoustics and optics benefit. The labyrinth of pores can damp sound and scatter light in useful ways. What about fire? Silica itself doesn't burn and tolerates high temperatures, but commercial products may include binders or fibers that can char. And while a thin tile can block a flame for a short time, heat will eventually soak through. Insulation slows heat. It doesn't stop physics. Performance also depends on pore size, humidity, and pressure. At very low pressures, gas conduction vanishes. At high humidity, some aerogels need hydrophobic treatment to stay effective. Cost has been a limitation. Supercritical drying isn't trivial. That's why much of today's market uses granule and blanket formats. Tougher, easier to install, and more affordable at scale. Research keeps pushing alternatives like ambient pressure drying and new polymer chemistries to cut cost and boost toughness. So why does aerogel look like smoke you can hold? Because at the nanoscale, matter becomes mostly surface, hundreds of square meters per gram, wrapped around tiny pockets of still air. That structure bends our intuition. A solid that's almost nothing, yet strong enough to protect a rose from a flame and efficient enough to keep rocket propellants cold. Aerogel is a reminder that when you engineer empty space, emptiness becomes a tool. Control the pores and you control heat, mass, light, and sound. It's proof that in material science, sometimes the most impressive substance is the space in between. If that made you think twice, Subscribe for more science that flips what you thought you knew.